as the examiners. Now I request Ancy to proceed.
So good morning to everyone present here. I'm here to present my research work on the topic Big Data Streaming Analysis under the topic Adaptive Ensemble-Based Streaming Data Learning Model for Handling Imbalanced Data and Concept Drift. So, big data. Big data is a term that is coined to have the collection of data that is very huge in volume, which is able to capable of handling variety of data like structured, unstructured, semi-structured, and which is able to take up high velocity of data. So when you talk about big data analytics, the processing is done in two ways, like batch processing and streaming processing. So batch processing, where the batches and chunks of data is processed. On the other hand, the streaming data is something which has very high speed, continuously arriving data, which wants the data to be processed almost in real time, which is semi-automated in structure. So in that case, understanding or analyzing of streaming data analysis, there are various techniques employed. So one of the best among that, or one of the most appreciated one among that, is sampling. So sampling is a process where you take up a set of representatives which is going to represent the entire data sets for the process. So the main disadvantage of sampling, or the challenging aspect of data streaming analysis, is imbalance in the data. Imbalance in the data is like you're not able to scrutinize the data into categories of classes. The classes are undefined, so you're not able to identify the elements in terms of groups. So you call it as imbalanced data. So sampling is one of the effective technique that is used to overcome the problem of unbalanced data. Another challenging appearance of big data streaming is that concept drift. So drift is a process where you have the sudden change in the flow of data. Usually the data are analyzed with reference to the patterns. So if there is a sudden change in the pattern, that makes the process to be difficult to understand and difficult to process. So that is where the concept drift plays a role. And the best useful technique to overcome this drift is making an ensemble classifier. So in this research work, I'm basically planning to I've handled the unbalanced data as well as the concept drift. These are my literature surveys with respect to the work which I have here, which is the gradual resampling ensemble paper. It performs basically a resampling of data, but it works mostly on the understanding of the previous arrived minority classes rather than neglecting the present minority classes. So that is the challenge over here. And when you talk about the adaptive sampling scheming technique, which is by Wei Zhongkon, it is one of the good paper which is able to handle imbalanced data through a reliable, predictable method, but fixing up the reservoir size, that is the fixing the size of the sampling, is a challenging task over this particular paper. And the third is recursive binary partition based sampling algorithm, which is basically used in this Cristino Carvela's paper. It handles concept drift as well as it is able to take up a bit of this unbalanced data, but it was not able to process the heterogeneous data, that is the data from different inputs like your unstructured and semi-structured data, was not able to successfully handle over here. And the third paper, the classifying imbalanced data, which use the algorithm dynamic feature group weighting framework with importance to sampling. So this is one of the challenging paper which I went through, and this paper is one of the reference paper which I have kept as a baseline for my research work, and it has the benefit of handling the drift along with the imbalance factor, but it was able to take up only the imbalanced class sampling from the previous data rather than the present oncoming current real-time data. So that is where it falls up, but though it produced very good results, I have taken this as one of the baseline for my research work. The next paper, which works on the algorithm knowledge maximized KMV, it combines both batch processing as well as sampling, like streaming data processing. But the ensemble classifier, the updation of the classifiers in the ensemble is manual and it is not an automated one. So this is the disadvantage of this. And the next paper is forgetting parameter extreme learning machine. FPELM is the algorithm used in this particular paper, which works mostly on the online learning, which is able to handle imbalanced data, but was not able to take up the sudden changes. It was able to process for the gradual change, but not for the sudden change. The next paper, which works on G-means update ensemble, this is again one of the interesting paper which handles both imbalance as well as it takes care of oversampling. But with respect to the unbalanced factor, something called as imbalance factor, which is calculated in the process, it was not as efficient as what we have achieved in my research work, and somewhere it lacks in taking up the minority classes into consideration. And next paper is batch weighted ensemble. So it applies incremental learning. It works on the ensemble classifier. It was able to update the classifier, but it was not as far as the previous existing blocks, where the size of the sampling, determining the size of the sampling is again a challenging task here, and hence it was not able to take up the minority classes, which is the base of the sampling. So based on these difficulties, or based on these limitations which I've seen in the research work, I've sorted out certain things as my research gap, where I worked on something called as oversampling to make the oversampling effective, as I found there was a gap in the oversampling, which is ineffectiveness, and I wanted to improve the classification accuracy too, so that I can handle the concept drift in a better way. And also, I try to work on the classification accuracy in dynamic environment than in batch processing. I wanted to do this as a real-time processing, which I found as one of the lag in the found as one of the research gap. And the ignorance of the minority classes was one of the biggest research gap in many of the research papers which I went through. So based on this, I have formulated and aimed to describe certain things, which is one, the first part is sampling, to extract a significant amount of stream representatives from the big data so that I can improve the prediction accuracy. Second, to handle the imbalanced data so that I can handle the imbalanced data as well as the concept drift in continuous arriving data, which is very high velocity, which I say as streaming. And the third, the research gap also falls for storing of the data. Since it is big data, the amount of repository that is needed to store this data was very high. So I have worked on this particular problem, and I have framed and converted this particular storage into some form of bitmap representation, making that the pattern matching an efficient one. So these are my problem statements, based on which I have worked on two basic algorithms. The novel methods, which I call one as HIDC, handling imbalanced data with concept drift, and the second one is streaming data mining on the fly using adaptive online learning model, which I acronym as SOAR. So these are the two methods, two novel methods, which was designed by me for this research work. So the HIDC method, the very first method, deals with imbalance class. It is able to handle the imbalance class. It handles the concept drift by selecting the samples. So it works on estimating the sample size beforehand using dynamic and static reservoir size, and the estimation of imbalance factor was a key part of this, with which with the effect of this imbalance factor, I was able to do a better decision or whether to perform oversampling or undersampling of my data set. And based on this impact factor, I was also able to frame a very good ensemble classifier, which eliminates the classifier which is not good for that particular data, which has the concept drift. So this is my first methodology. And second methodology, SOAR, which actually aims in prediction of the new concept. Like it has a set of patterns that is being present in the repository. At certain point of time, these repositories are in bulk, and the pattern matching here, I've converted that into something called as bitmap representation. And these bitmap representation with these patterns, I'm able to form an ensemble classifier, where the classifier updates itself automatically based on the voting system. So the classifier either deletes an inactive classifier or adds an active classifier and converts a state between active and inactive states, so that it better takes care of the imbalance and the concept drift. So HIDC, so it focuses both on data pre-processing, stream or classing analysis. So the very first step over here is deciding the optimal reservoir size. This I have done in two ways, one using dynamic sampling, another using random sampling. In dynamic sampling, based on the changes, that is the drift that occurs, and based on the source of the data which I have attained, I try to frame the optimal reservoir size dynamically. That is, the samples are created dynamically with the reservoir size, which is dynamically chosen based on the input of the data and the source of the data and the rate at which the data change. And random sampling is something which attempts to randomly take an optimal size which is not predefined. So based on the source of the data, it updates itself, and with the previous and the next data in the repository, it takes a decision and randomly it allocates an reservoir size. And once the reservoir size becomes full, it is able to either delete or update the reservoir size, increase or decrease the reservoir size based on the necessity of the flow. And with this reservoir size, I was able to calculate an imbalance factor. So this imbalance factor is a key aspect here with which I'm deciding whether my sampling was correct or not. So with this, I try to resample. That is, I try to either oversample my data or undersample my data. So based on that, I make a very good classifier depending on this oversampling and undersampling. This at end of the day, the classifier which I have decided based on this impact factor is able to handle this drift and imbalance data in an efficient manner. And the last part here, I have made an ensemble member updation. That is, again, as I said, with reference to the imbalance pattern, I was able to automatically update my ensemble classes, either to eliminate a classifier from the ensemble or to add a new one based on the imbalance factor. So the methodology works like this. The first part, whenever I get a pattern streaming data analysis, I work on the streaming dynamic sampling, where I design on the optimal size reservoir, either using random sampling method, randomly selecting the reservoir size or dynamically allocating the reservoir size. Once the reservoir size is fixed, I try to work on the disparity ensemble learning method, where the first step is to calculate the imbalance factor. So once the imbalance factor is estimated between the previous and the current scenario, I decide to do whether it has to be oversampled or undersampled. So based on this, the training process of the training process will take place. And once it is done, once the disparity measurement is completed, I work on updating the weight for the ensemble classifier, with which the classifiers, the members of the ensemble classifiers are determined, and at last this particular ensemble classifier is able to handle the diff concept very efficiently. So for this HIDC, I have used STROM, which is one of the machine learning database which is available, which is similar to Hadoop, and the programming language I will use is Java. And I've taken the city of Azaras from August 2014 to September 2014, the climatic weather condition as the parameters here. And my feature which I have used is timestamp, the location, the temperature, the dew point, and things like that, which is like the streaming data, which is going to have n number of drifts in over it, and I'm trying to handle these drift and imbalance among these particular data set, which is using my HIDC approach. The baseline of my work is dynamic feature group weighting framework, which I said actually one of the reference paper which I had in my research literature work. There are various parameters or metrics that is used to evaluate the imbalance factor and the drift concept. So the first one is the precision. So precision is something where I try to calculate the false positiveness of the samples. For example, if I'm going to take a set of samples, I'm going to find out how many samples are going to give correct results out of the total return results. The recall in turn is going to give me how many samples are going to produce me a correct result with the result that has to be positive. So this again, these two parameters are the main metric which is used to identify the quality of the imbalance data. And G mean. Okay, before G mean, F measure is the weighted harmonic mean of the precision and recall. So the entire system, the quality can be measured with this F measure, and G mean is used to calculate the false negativeness. So recall and precision is working on false positiveness, and G mean is the one which is used for false negativeness. There is two things called as sensitivity and specificity. So G mean is the approximate geometric mean of these two classes. So when I try to bring, these are my results which I have obtained in real time with the working with the process. So when I try to calculate the precision with respect to changing the minority classes, so the DFGT WDSS, the WIS work started with giving a good efficiency of 73%, but in long run, when the number of minority classes increase, it falls below to 62 or 63. But by method, which is represented in a blue line, the HIDC method produced an efficient result which started from 85% and maintained a stagnant of 80%. When I try to draw, when I try to work with the recall, what are the negative false negative categories which is actually obtained, the existing method fall down to 60, and even below 60 if the number of minority classes was increased, but at the same time my result, my work with HIDC able to maintain a sustain of 85 to 90% in average even with the increase of minority classes. So this is the biggest advantage of this method, where when you take up the different minority classes into consideration, you will be able to handle the imbalanced data in a better way. So HIDC improves the recall by 29.15% more than the existing method. So when I try the G mean, that is the geometric mean, what are the false negatives? The number of, with respect to the concept drift. Okay, in the previous session I was working with the number of ensemble classifiers. Here it is with the number of drift over time. So my existing method, which I have taken as the baseline, fell down to 40 degree of efficiency for G mean because it was not able to handle different concept drift because it eliminated the minority classes. But my method, which is HIDC, was able to maintain a stagnant of again 80% efficiency, which is good to know when compared to the current method. With respect to the number of instances per hour, the DFGC improved a while and maintained an average of 50% with increase in instances, but my method HIDC was able to produce efficiency of 75% and it improved as the number of instances increases. This is because my system was able to understand the different patterns with learning more on the minority classes. So once it learned more the instances it was able to perform far better than the previous cases. So F measure was increased by 15% when compared to the previous existing one. Okay, the second method is SOAR. This is like it is going to handle the data on the fly. The very first part of here is going to adaptively selecting the window size by its size, that is the sample size is being adaptively selected based on the patterns which is stored in the repository. So it stores the pattern in the repository in the form of bitmap representation, and based on that it is going to take up the present data, understand it, analyze with the pattern which is present in the repository, and decide on the adaptive sliding window size. And the second point here is it automatically updates the classifier, members of the classifier. So ensemble classifier is one which consists of more than 2 or 3 classifiers together work to solve a particular issue. So updating this particular classifier, updating this particular ensemble with different classifiers is again in most of the cases were manual. In some cases it was static, but here it works dynamically by updating the classifier and deletes the unwanted classifier in the long run. And fast ensemble classifier using correlation pattern, the storing of the bitmap. So for updating of the classifier, I use the weight for each classifier, and the classifier weight is updated, and based on the weight, the active classifiers and inactive classifiers are being identified. The active classifiers are the one which is the new pattern. The old inactive classifiers are the one which are the old patterns. So these patterns are everything are stored in the form of bitmap in the repository, and based on that I'm going to update the ensemble classifier. Either I'm going to remove a classifier or delete or update a classifier, or even change the state from active to inactive one in my current system based on the weights which is allocated, and this weight in turn is calculated by the voting system that is a reflect in turn of the sudden change that happen in the sampling system whenever you get to know a new pattern. So this particular system reacts for that particular change and updates the ensemble classifier. And as I said, if the entire system is going to store the complete repository in the form of bitmap representation, which again commercially is going to save so much of money and time, which is in better advantage of this particular system. So this particular system understanding, I've tried to understand the query. So whenever a new input is being raised, so this particular query is being given to the query processor, and based on the query, a new pattern is being generated, and this pattern is being given as an input to the adaptive window. And based on the adaptive window, an ensemble classifier is designed, because we have the pattern in hand, and with the pattern we are calculating an adaptive window based on the voting system, and ensemble classifier is designed. At the same time, the query is also replicated to the historical, like the repository where the data are stored in the form of bitmap representation. And once it is done, this ensemble classifier will get back to the repository and check whether this particular pattern has happened already or not. If it has happened, it is going to return the data from the repository. It is not going to recalculate. It is not going to reframe the ensemble classifier, which saves time. But in case if it is not there in the pattern, it is going to update the classifier and again store it back to the repository and give and respond to the input which has been obtained in the form of query. So this is the overall architecture of SOAR method, and here I have used Apache Storm and SOAR as the database, the library, machine learning library, which is used for this process. And here I have again used the data set of the weather forecast data set from the synthetic weather data line. And these are my two baseline works, like ensemble model and adaptive windowing model. And here again I've taken precision, recall, and F measure, and the delay in consideration as a metric to evaluate the quality of my SOAR algorithm. So delay, this is one of the factors, because like in real time when we use it in commercial purpose, this time complexity and space complexity is one of the challenging tasks in IT today. So here I've taken that also into consideration for one of the metrics. Okay, for understanding or analyzing my SOAR, I've divided this part into three classes. One, I tried my SOAR by changing the number of ensemble classifiers. Case 2, I try to understand the performance of SOAR by varying the number of diffs. So first is number of classifiers is updated. Case 2, the number of drifts over time is updated. And third, by number of instances while sampling. So by varying the number of instances. So case by case, three different cases I try to evaluate my SOAR. So case 1 with number of ensemble classifier, my EM method, it falls from 60 and falls down when the number of classifiers increases. And AOWE, again the method same, falls down to 60, below 50, but my SOAR method was able to reach 95 and then to maintain an average of 65 and maintain an average of 65 till the end, when the number of classifiers get greatly increased. Okay, so when so this SOAR has produced better performance of 28% when compared to the existing method. So now recall. So when I talk about negatives, false positiveness. So again the EM falls below 50% as average, like below 55% as average. AWE again increases with the initial classifier setup, but in long run again it stays to 60 as the average value. But my SOAR was able to start with 70, reach up to 98% of efficiency and return back to 68 to 70% as an average with an increase in the ensemble classifier. So here my SOAR has outperformed AWOE method by 25% and EME method from with 30% with differences. And with respect to F measure, that is the harmonic mean of precision recall, when compared to the ensemble classifier, the EM method falls below 50 to 55%. The AWOE method again try to take up the changes, but again it falls down. But SOAR was able to actually perform well than the existing systems and maintain an average of 55 even at the long run, with increase in the ensemble classifier up to 6 or 7. So the time delay keep on increasing with the increase in number of classifiers with respect to the existing system, but when comparatively my SOAR was able to produce very much less delay in response with respect to the existing system, which provides far better than the existing one. So sudden increment of the execution time of EM was drastically went to a point of infinity at certain issue. The second case is that I'm trying to vary the number of concept drift over time. So with respect to number of drift over time, my precision, that is the identification of the false positive, started with a good efficiency, but later fell down to a degree of 60 or 65, and AWOE, it showed a gradual influence, but it was not able to outperform after a percentage like 75%. But when we talk about SOAR, it initially started with very good of 95 or 97% and gradually maintained as a sustained result throughout, even when the number of concept drift over time increases. So, with along to recall, the graph of EM falls down. Since the main reason the fall down of EM is that it doesn't consider the minority classes in the time, and the pattern matching was not a historical pattern matching, hence this happened. So again, AWOA, it showed an improves, but it was not able to produce efficiency above 75%. But again, the SOAR was able to maintain 98 to 99% of efficiency throughout the process. So recall of EM is degraded by 26%, but our SOAR method was able to maintain an average performance throughout this process. And F measure, again the EM drifted over time. The AWOE showed an increase which maintained up to 75% over here, which was 65 in the previous cases, but in F measure it was 75. Again, the SOAR was able to outperform and it maintained an average throughout the process, even when the number of drift over time increases. So the delay with respect to AWOE and the remaining system, the delay was very, very less with SORs when the number of concept drift have been changed. So this is an interesting part of the SOAR and better advantage when compared to the existing systems. So the case 3 is varying the number of instances. So this instances, the varying the instances happens in the form of sampling. So whenever these instances per second per minute, like what got changed, this EM tried to improve the efficiency, but at a certain point it was not able to perform after the percentage of 75. After that, it started identifying the false positives wrongly. But AWOE, it was able to perform to about 88%, but so was like even it performed very good with very number of instances and outperformed even with the instances very high up to 1152 instances per minute. So this is like where it proves to be very efficient when compared to the existing systems. And the recall method, the recall when compared to the number of instances, again both the cases were trying to improve but not above 95, whereas the SOAR was able to produce 99 efficiency with respect to the recall when we able to find out the number of instances. When more number of samples were exposed to the system, it was able to have a better prediction on the drift as well as the handling of imbalanced data. So the F measure calculation with respect to EM, it gained, and at a certain point of time, since the minority classes were neglected, as I said already, it was not able to handle thousands of instances. It failed to handle, it dropped down tremendously. But with respect to AW, it was able to maintain an average of 88%, but our SOAR outperformed and maintained again a 98% of efficiency, even with higher number of instances, F measure. So the delay with respect to number of instances were very much reduced when compared to the existing systems. Because the number of instances are so much and high, it was able to actually do a better performance when compared to the normal one. So the overall conclusion of my work is on HIDC. I have decided to efficiently handle the imbalanced data by decision making, by evaluating the imbalance factor. With respect to imbalance factor, I use a weighting mechanism to update my ensemble classifier and have produced and approved 29.15% higher recall rate. Overall, 43% better performance than the existing DFGWIS approach. So this is one of the questions raised by the examiners on my thesis, like to compare the difference between the current system and that. The second methodology of my system is SOAR, which works on online learning rule, which updates itself with the patterns. With different diverse classifier members, it was able to update the classifiers, change the state from active to inactive one, and it outperforms the existing method by the recall rate of 97 to 97%, even when it had a great number of concept drift. So this is my research work is about HIDC, which performed 43% better, and SOAR, which was able to produce 99% results. And these are my publications, I have one publication in Taylor and Francis, online learning model for handling different concepts in cybernetics and system, and another second publication in elsewhere in computer communication. So these two papers are successfully published. And the examiner's question, which was raised on the thesis evaluation by the examiners, was these 4 questions. So I wish to answer for these questions like in a brief. Motivation to start this work. Okay, so to start this work, when I was doing my PG, I was working with the real-time data of Regional Meteorological Center, the Government of India, the weather forecasting department is in college. So when I started working with them, I tried to understand, I came to know what is the reality happening in the world around. Like everything is imbalanced, nothing is balanced, where we learn theoretically like this is classification, we classify in class C, we classify in class B, but that is not the fact with reality. So it comes back to thing which showed me like there is so much of imbalance in the data around us. So that was the basic motivation behind this. And when I started learning on the research paper, I came to know that streaming data analysis is the place where this particular sorry to interrupt. Okay, so when I started learning more on that, the streaming data analysis was a challenging place to have this imbalanced data. So that was the basic motivation of this research work. And the commercial value of the work. With respect to any organization or any world today, the growth of industry, right? So it is going to have a greater impact on the space complexity and time complexity. With respect to that, as I mentioned, my SOAR methodology was able to is able to store the data in the form of bitmap representation with safe space, and in turn the delay calculation was also made as one of the metrics, which certainly proves far efficient than the existing system. So when the time complexity and space complexity is considered, it contributes actually too much to the commercial value. And in real time, the fraud detection, the anomaly detection, the network intrusion detection, even in medical field of analysis of this live blood cells analysis and things, everything, all these together is contributed to the base work of this. And together with this, I'm able to say that my work have efficiently contributed the commercial part of the value, where it is able to prove a challenging part in space complexity and time complexity, and justify why the percentage was drastically down from 95 to 60% in number of ensemble classifier with precision analysis. So that I have in the form of graph 2, which says since we don't have the minority classes considered, so that particular question was about this part, where the precision okay. I'm trying to share my screen with the graph, so just 1 second of time for me so that I can explain that concept. Okay, so I guess my screen is visible now. So here the question was with this, what was the reason of my fall? I think my screen is not presenting now, so 1 minute, I'll try to present my screen. Okay. Able to see my screen now? Okay, so this is a place where the question was raised, why there is a sudden fall from 95 degree to 60 degree in the cases of ensemble classifier. Okay, so this is because when your system has got trained to the classifier, so at one certain point, the initial state, it is able to learn, it is in the learning phase. So once a classifier starts learning, in the learning phase, it reaches to 90 degree, but once these patterns are stored, as I said, it is there already in the background for the verification. These patterns are the classifier is able to predict a pattern beforehand. So here it is not again to trying in the certain position to find out which are the false positives. Instead of, it is working on to identify the drift and update the classified. So that is the point why this has been fall down. But actually, this is the learning curve. So from 60 to 90 and 90 to 60 is the learning part of the ensemble. Once these patterns are updated to the repository, in long run, it is maintained an average. After that, it is not fallen below 65%. It is able to maintain an average till the end when number of classifiers are being taken care of. And the last question, which was posted, is my screen visible now? So the last question which was posted to me is, describe the performance difference in HIDC and DFGWIS. As I said, the HIDC method, which is a novel method which has outperformed this DFG, the overall approach of 43%. So the main reason behind is that we have considered the minority classes into consideration. So this GWIS method was able to work out only with the previous pattern for the current drift. But we didn't do, like the HIDC did not work in that way. It was able to frame a pattern for the current drift and able to handle it. So which was like almost as an average with the precision recall metrics, it was 43% better than the existing method. So these are the various questions which was posted to me like in the thesis evaluation, and following which are my references. So I had n number of references. Here are a few which I have listed out, and thank you so much for your time, and I like to take the questions if any.
I request the examiners to